Okay, so we have a frame that's supporting a 100 Newton load in the manner shown. Neglect the weights of the members and determine the reactions at the pin at A and the pin at D. Okay, so the first thing we want to look at is we do have a pin here at A, so we're going to have an AY and an AX, and we're going to have a pin here at D, DY, DX. And upon investigation, we have 1, 2, 3, 4 unknowns, and so far we only have 3 equations of equilibrium, okay? But that's where that internal pin comes into play at B. We can take it apart, and if I can take it apart and lay it out as 2 separate pieces, it's like adding an additional equilibrium equation, okay? The other thing I want to take note is this is a 2-force member, and that always makes things easier too. If it's a 2-force member, I know that it's either in tension or compression, and so when I look at this member, okay, BD, that's at 60 degrees, okay, I am either in compression or tension, and my forces that are acting at B and D, the resultant of those at the pin have to be passing straight through that member. It's a 2-force member. So when I look at that, I can see that dx and dy are going to be components of that reaction at D. Okay? So if this is 60 degrees, this has to be 60 degrees. So dx, okay, another way to write that would be d cosine 60. dy, another way to write that would be d sine 60. I can't say the same thing for A. I cannot break A up and use the component form. This is not a 2-force member. So I can't just say that the resultant force at A is pushing back up through the centroid of that member AC, because we have a pin and we have an applied load. So it's not going to work out so sweet. But a 2-force member, remember, there's no loads on it. And so as such, it's either a tension or compression member, just like in a joint, which means my reactions at the ends, again, have to break down. And if this is a compression member, then I'm pushing on that member. And I know that the reactions are going to be some sort of a ratio, if you will, of this relationship of the 60 degrees that the member is to our XY world. Okay? So we're going to go ahead and just start with a free body diagram of AC. And I'm going to use my straight edge, or just try to be very, very neat. And when I look at this, I have 800 newtons. I have at A pin, so I have an unknown AY, an unknown AX. If I want to look at this, this is like a giant triangle. And I know that this is 30 degrees. So if this member here, okay, if we are 650 millimeters and 300 millimeters, then I can look at this y dimension, and I have sine, so opposite of 30, equals y over hypotenuse, 950. So this distance y has to equal, I lost my calculator. Okay, so we have 30 sine times 950, and I get that y has to be 475 millimeters tall. When I look at the total x, okay, the total x right here, then this total x is going to come from cosine 30 equals x over 950. So that total base has to equal 30 cosine 950 times 823 millimeters. Okay, and then I'm going to recognize that this is actually a 2-force member, so it's going to be, it's in compression. Okay, normally I would assume tension, but I'm going to just assume that right now. And I know that really, you know, when I look at this coming in, it breaks into X and Y components. But we're just going to look at that whole piece of being BD. And if we sum our moments about A, okay, then I'm going to have BD, okay, that member force BD, times 650 millimeters, okay, and now I have this 800. And I can either break it into x and y components, or I know that it acts along this vector line, and its perpendicular distance is this distance x, minus 800 newtons times 823 millimeters equals 0. So if I take this 800 times 823, I bring that over here, it becomes positive, and now I'm going to divide it by 650. And I get that BD is indeed 1012.9 newtons, and it is in compression like I assumed. Okay, so I found that compressive force. And now I have several different ways I can go back and find my reactions. I can look at my two-force member. BD, and when I look at this two-force member BD, I know that if I'm in compression, okay, I'm actually pushing back in on that member, and I have 1012.9 newtons. That means when I'm looking down here at joint D, I'm in compression at 1012.9 newtons. I also know that I am at 60 degrees. So my x and y components of my reaction at that pin have to be pushing back equal and opposite. So dx equals d cosine 60, which we've already said, and dy equals d sine 60. So I can take 1012.9 sine 60 times, and I get that my y component is indeed going up at 877 newtons in the direction that I assumed. And for dx, I have 101, we're going to swap, and I can take cosine 60 times, and I get that dx is 506 newtons, and it's pushing back to the left. And because this is a right triangle, I should be able to square both of those, square plus square root, and I end up back with that member compression, that force in the member that's a compressive force. Okay, so here I could go and I could look at an overall free body diagram, and I would have values for dy dx, and I could sum forces x, y, and get values for ax and ay. Or I could continue here looking at this segment from A to C if I know that BD is a compressive member, okay? So it's pressing down on the joint, which means it's pressing back up on that pin. This is going to have x and y components of cosine 60 and sine 60. So I could continue with this piece here, and I could sum forces in the x direction equals 0. And I have my AX that I've assumed is going to the right. I have this member BD, it's in compression, it's pushing back up just like method of joints on a truss. And if I look at the x direction, okay, if I look at the x direction, it is going to be the cosine 60. So I have minus 1012.9 cosine 60, and that's all I have in the x direction. Okay, so AX has to equal 506 newtons, pushing to the right like I assumed. Now we can sum forces Y. Okay, and I have AY going up, compression, pushing on the joint this way, so our Y is going up. So we have plus 1012.9 sine 60. Okay, that's the y component. And then we have this minus 800. And all of that equals 0. So let's 10, 12. Okay. 60 sign times 800 change sign minus, add those together, and I get AY So if this is an 876 that's positive minus 800, that's a positive 76. When I take it over here using algebra, I get negative 77 newtons, okay? Which means my AY is actually heading down, okay? So I assumed it in the wrong direction, which makes sense. If I am pushing up here with that compression member, this is going to want to go up, and this is pushing down. So it's going to want to like flip. I'm going to have AY pulling it down to keep it attached to the ground. Okay. So how can I make sure that this is correct? Well, I can look overall, and I've got DX going to the left and AX going to the right, the same values. If I look at my picture, the only thing in the X direction are AX and DX, and they should be equal and opposite. Okay? If I look overall, I have C coming down at 800 newtons, and I have AY coming down at 77 newtons, and then I have DY pushing back up at 877. So if I look overall, I have 877 up at D, and then I have the applied 800 and the applied 77. So when I sum those overall, I get that the sum of the forces X, 0 equals 0. And if I sum forces Y, I get 0 equals 0. Check, check, smiley face, smiley face.